As the MD-83 soared high above the southern Sahara, distracted by events outside, its crew failed to notice the subtle yet potentially catastrophic change in circumstances, which were, by now, hidden directly in plain sight. As the point of no return was passed, the aircraft and all 116 souls on board entered a deadly spiral dive, impacting the desolate desert sands below, a mere 50 seconds later. This is the chilling tale of Air Algérie Flight 5017.
Calling out Mayday.
In the early hours of July 24, 2014, while sitting on the ramp at Thomas Sankara International Airport, Ouagadougou, in the West African state of Burkina Faso, the two cockpit and four cabin crew of Air Algérie Flight 5017 readied their McDonnell Douglas MD-83 for its return leg to Algiers, capital of Algeria, with an anticipated flight time of in around 4.25 hours. Ahead of them lay just over 2,700 kilometres or 1,700 miles of bleak, inhospitable and desolate desert terrain, the Sahara, the largest and hottest desert on the planet. However, as the saying goes, every cloud has a silver lining, and in this context, it's the very meteorological phenomena which gives rise to this desolation that also contributes to a generally stable air mass above it. In other words, they could look forward to smooth flying conditions having reached their cruising level, but there was still a bit of work to be done before they could settle in and relax. In climbing to the north out of Ouagadougou, initially over the Sahel region, which forms a transitional zone between the fertile belt of humid savannas to the south and the arid Saharan landscape to the north, they would first have to traverse the Intertropical Convergence Zone, more commonly referred to as the ITCZ. In meteorological terms, the ITCZ is a band of near-perpetual thunderstorms which circumnavigate the globe at equatorial latitudes, having a tendency to move slightly northwards during the months of June to September. In the case of Western Africa, this frontal area is created as a result of conflict between the masses of dry area over the Sahara and those of the moist Atlantic Ocean. This contrast giving rise to the development of thick, convective cumulonimbus clouds with accompanying heavy rainfall. In this part of the world, this monsoon-type activity is often associated with violent squall lines which cross the African continent from east to west at intervals of 3 to 5 days, a phenomenon colloquially referred to as the easterly wave. Indeed, on the night of July 23rd and into the early morning hours of the 24th, this was exactly the situation as an active wet front moved slowly across Burkina Faso and into neighbouring Mali. The activity of these waves is subject to diurnal variations, developing between midday and late afternoon, and reaching a maximum through the hours of darkness, only to weaken as the dawn approaches. Fully mature, the physical size and area covered by these thunderstorms shouldn't be underestimated. Horizontal dimension can be hundreds of kilometres in magnitude, with vertical development extending up to altitudes of 15,000 metres, or the equivalent of 49,000 feet. As a general rule with thunderstorms, the higher they grow, the more dangerous they become. Although the subsequent accident report into the events surrounding Air Algérie 5017 will not make any references to whether or not this convective activity had caused the crew any particular difficulties on their transit south into Ouagadougou, unbeknownst to the crew and all 110 passengers on board, it most certainly will on their way back north. Although the flight was being conducted under an Air Algérie flight number and call sign, the aircraft was in fact only on lease to the company, along with the 6 crew members on board. The MD-83 was actually listed on the Spanish registry as Echo Charlie Lima Tango Victor, being owned by the Spanish operator Swiftair. Swiftair, who was a Spanish charter airline founded in 1986, with its headquarters being based in the Spanish capital Madrid. Unlike regular commercial operators, back in 2014 the airline didn't sell tickets directly to the open market. Instead, it ran on-demand ad hoc cargo charters and organised wet lease operations. These by definition being arrangements whereby the airline offered services for hire to other third parties, a complete package which included aircraft, crew, maintenance and overall insurance. Indeed, the whole operation was actually conducted under the terms and conditions of Swiftair's Air Operator Certificate, or AOC, which had been issued by the Spanish regulator. The third-party airline involved in this instance, Air Algérie, was simply responsible for the commercial aspect of the business, namely seat sales, marketing, handling fees, and route structure development. Historically, such ventures had led Swiftair to carve out a unique existence for itself in parts of the world, which most traditional European airlines would have shied away from. It had, in recent years, cultivated extensive operations throughout the Middle East and Africa, while also flying for many years on behalf of the United Nations mission in Sudan. In the context of their arrangement with Air Algérie during the summer months of 2014, the African carrier had approached Swiftair in order to secure additional capacity, so as to supplement their own passenger fleet during this busy travel season, with the intention that the aircraft and its crew will be based in Algiers for the duration of the contract. Generally, the relationship between the Swiftair crews and Air Algérie staff was considered to be extremely positive, and reports indicated that both worked well together. On the night in question, the flight dispatcher in Ouagadougou had stated that pre-flight, the crew appeared calm and conscientious. He had presented the crew with their standard flight dossier for the return leg to Algiers, containing an up-to-date weather report, a list of operational notice pertaining to the intended route of flight, and a provisional weight and balance summary, which, he said, the crew had examined attentively. In the left-hand seat and in command of the aircraft was one Captain Agustin Comaron Mogio, age 47, both an instructor and certified examiner on the MD-80 series of aircraft. He had amassed a grand total of just under 13,000 hours of total flight time, 10,000 of which having been obtained on this particular type, more than half of that in command, with the Air Algérie contract having commenced a mere 4.5 weeks beforehand. The flight that evening would have only been Captain Mogio's second visit to Ouagadougou during that time frame. However, that said, between 1997 and 2012, as first officer and then captain with another Spanish operator, Spanair, he had accumulated a significant amount of experience operating into various North African destinations, Ouagadougou included. Having left Spanair to join Swiftair in June 2012, he had accumulated an additional 450 hours or so as captain on the MD-83 while operating under contract for the United Nations, based out of Khartoum in Sudan. So in other words, Captain Mogio was no stranger to the various challenges associated with operating transport aircraft in this particular part of the globe, and certainly the unique weather patterns associated with these latitudes would have been all too familiar. His first officer that fateful evening, although understandably less experienced, had nonetheless accumulated just over 7,000 hours of flight time in her own right, nearly 6,200 of which having been attained on this particular type. Age 42 and also a Spanish national. Her name was Isabel Ghost Chiamari. Since commencement of the Air Algérie contract, she likewise had only visited Ouagadougou once previously, and that coincidentally had also been with Captain Mogio only the day previous. Again, with a background similar to Mogio's, she had also commenced her flying career with Spanair in Spain, and had likewise gained a lot of experience in West African operations during the 14-year period she had spent with the airline. Although only 2 of 6 pilots based in Algiers that summer, they had nonetheless been rostered to fly together almost consistently since commencement of the contract on June 20th. 43 flights to be precise, totaling over 93 hours of flying time. So it would be fair to say that they knew each other well, and nothing in the subsequent report would suggest that their working relationship was anything other than professional and positive. A file containing the meteorological data in force at 22:30 Zulu, coincidentally the same as local time, was handed to Captain Mogio on his arrival into Ouagadougou. It included, amongst other things, both actual and forecast weather reports for airdromes along his intended route of flight back north to Algiers, a satellite infrared chart of the convective weather to the north, and a specific SIGMET, or Notice of Significant Meteorological Information, valid from 20:30 on the 23rd to 1:30 a.m. on the 24th, the latter part of which would still have covered the time of their intended departure. This notification warned crews of embedded thunderstorms moving west-southwest across a large portion of Western Africa, from Niger to Senegal, and encompassing the Gossi region, the area of southern Mali over which they would fly while heading back north to Algeria. All this, plus the fact that just a little over an hour previously Mogio had flown south through the very same area, meant that the crew of Algérie 5017 were acutely aware of what lay ahead of them as they prepared the MD-83 for its departure. With boarding and all these pre-departure preparations now complete, just after 1 in the morning local time, the crew of Air Algérie Flight 5017 requested and were clear to start engines, in anticipation of a departure from Ouagadougou's southwesterly runway 22. Shortly after the crew commenced taxi, some 10 minutes later, the controller on duty, who happened to be working both the ground and the tower frequencies simultaneously, given the light volume of traffic at the time, issued 5017 with its anticipated departure clearance, a clearance which, although more expeditious in nature, differed considerably from the one which they had been expecting. The route back north to Algiers, which had been filed sometime earlier that evening, had 5017 initially track out to the east after departure towards Niamey in Niger, before turning north and proceeding along airway Upper Mike 608 towards the Rofer intersection. In contrast, however, on receipt of their departure clearance, they were instead actually cleared to make a right-hand turn after departure, proceeding directly towards the Apepo waypoint, which, despite being a more direct and expeditious routing back to Algiers, would actually bring the aircraft into airspace where it should never have been, and was in fact prohibited from entering. Specifically, to enter the airspace concerned, all two-engined aircraft had to be ETOP certified, a certification standard which Swiftair had not sought for its fleet of MD-83s. ETOPS stands for Extended Twin Engine Operations. In short, what this means is that such designated routes, being inherently remote in nature, and thus not supporting of many en route airfields, require that any twin-engined aircraft intending to enter that airspace be maintained to a much higher standard than is normally the case, in order to mitigate against the possibility of any in-flight failure which might ultimately require the aircraft to land en route. In this instance, being non-ETOP certified, 5017 was thus obliged to stray no further than 60 minutes flying time from any usable airfield along its intended route, and the routing back to Algiers had to be planned accordingly. Hence the initial intention to have the aircraft route east after departure, in order to assure compliance with this regulatory stipulation. In reality, the controller was most probably unaware of the aircraft's non-ETOP status. Indeed, on its early arrival into Ouagadougou, although being unapproved to do so, it had actually routed south through the very same intersection, and he was thus most probably just trying to facilitate 5017's most expeditious routing home. Furthermore, subsequent interviews with ATC staff in Ouagadougou highlighted the fact that their radar equipment was incapable of painting weather returns. So, in all likelihood, his offer of the direct routing to Apepo was made in complete ignorance of what lay out to the north. All that said, however, it was Captain Mogio's prerogative to accept or decline the clearance which he had been given, and in choosing the former, he would unwittingly seal the fate of his aircraft and all those on board. And so, just minutes later, at 1:15 a.m, in the early morning hours of July 24th, Air Algérie Flight 5017 finally got airborne. As it did so to the north of Ouagadougou, along Burkina Faso's border with neighbouring Mali, the thunderstorms of the ITCZ were now fully mature and at their most active, with Mogio's execution of the right-hand turn now putting them and his aircraft on a direct collision course. 9 minutes after departure, at 1:24 local, while still working the tower controller's frequency and climbing through flight level 145, 5017 transmitted their estimate for Apepo as 0138 local, with an arrival estimate into Algiers of 0506. With the storm cells up ahead now clearly visible and cutting an impressive outline against the featureless black Saharan landscape beyond. Just 4 minutes later at 0128, while climbing through flight level 215, 5017 was handed off to the en route Ouagadougou Air Traffic Control Centre. Having established two-way radio contact, the crew wasted no time in informing the en route controller that they were turning to the left in order to avoid weather which they had identified as lying directly across their path. This initial course correction amounted to 28 degrees of a left turn, followed shortly thereafter by 2 further turns to the left, the first of magnitude 4 degrees and then a further 8. A superimposed weather radar return of the actual weather encountered that evening allows for a good appreciation of the avoidance manoeuvres which the crew of 5017 were attempting to undertake. Believing their lateral displacement around the storm to be sufficient now, finally Mogio rolled the aircraft back onto a heading of nearly 020 degrees, essentially paralleling his initial track by some distance further out to the west. While still deviating around the storm, the aircraft's autopilot finally acquired the selected cruise level of flight level 310, the equivalent of 31,000 feet, with the outside air temperature being measured at a relatively warm minus 30 degrees centigrade. With the autopilot maintaining the jet's altitude, the autothrottle was now tasked with maintaining a cruise speed of Mach 0.74, or nearly 3/4 the speed of sound. From his position in the left-hand seat, Mogio leant forward and selected cruise on the thrust rating panel, located to the right side of the cockpit centre engine instrumentation. What this does is to force the digital flight guidance computers to calculate the EPR value limit based on the outside total air temperature, altitude and engine pneumatic bleed configuration. The concept of EPR, or engine pressure ratio, needs to be explained here, in order that you be fully able to appreciate the events which are about to unfold over the next few minutes. As a general rule, jet engine manufacturers use one of two established methods in order to represent engine thrust output. The first is a simple relationship between the engine compressor rotational speed, known as N1, and the thrust that the engine is actually producing. Expressed as a percentage, 100% N1 or thereabouts would equate to full power, whilst a value of 20 to 25% would usually equate to an idle power setting. With the second method, a pressure measurement of air entering the first stage of the engine's compressor is compared to a pressure reading of exhaust gases as they leave the low-pressure turbine at the rear of the engine, the differential between both readings being expressed digitally as a ratio, an engine pressure ratio or EPR. The greater this EPR value, the greater the measured thrust output of the engine. Specifically in the context of the McDonnell Douglas MD-83, Pratt & Whitney had decided to use the latter EPR methodology for the JT8D engines fitted to the type, despite also recording a displayed N1 value, but only in a secondary context. As such, the pressure of the air entering the engine's compressor section was measured by a single probe in the spinner or nose cone of the engine, this probe being referred to as the PT2 probe, while at the same time at the other end of the engine, the pressure of the exhaust gases leaving the turbine section was measured by a ring of 8 equally spaced probes placed into the hot exhaust gas stream, collectively referred to as the PT7 probes. The ratio between these two pressure readings, outlet over inlet, denoting the engine's EPR value. In the cockpit of the MD-83, presentation of EPR information to the pilot is twofold. Firstly, the current EPR setting or instantaneous thrust output of the engine is continuously displayed on a set of EPR gauges, one for each engine, located uppermost on the centre engine instrument panel. Secondly, just above these indications is located a readout of the maximum EPR value obtainable, given the current conditions and phase of flight as calculated by the digital flight guidance computers. With auto throttle engaged, as was the case with 5017 from the moment of liftoff, this figure provided a clear and unambiguous indication to the pilots of the maximum engine power available to it, that being the auto throttle, while working to achieve the target it had been set, which was, since the aircraft had levelled off, the maintenance of a Mach cruise value of 0.74. Confirmation that this was in fact what the autothrottle was doing was indicated on the aircraft's flight mode annunciator, or FMA, a small information panel prominently located in the pilot's direct line of sight. Two panels in fact, one in front of each pilot. Not only was the FMA designed to communicate active autothrottle modes, but also the active and or armed modes of both the autopilot and or flight director in both the lateral and vertical planes. In addition, the actual engagement status of all three, autothrottle, autopilot and flight director, was continuously monitored and displayed by way of separate indicators on the panel's face. Thus the FMAs were a live, continuous indication to the crew as to the aircraft's automation status and well-being. Within minutes of the aircraft levelling off, A small, almost imperceptible error at first had begun to manifest itself in the displayed EPR values of the right-hand number 2 engine. For no obvious or apparent reason, the power output of the engine was starting to creep upwards towards the allowable cruise limit, without, it appeared, any corresponding increase in compressor rotational speed. In other words, one gauge was showing that power in the engine was ever so slowly increasing, while another was presenting a completely contradictory assessment of the situation. 55 seconds after the right-hand engine had started to present with erroneous EPR indications, the left-hand number 1 engine had started to do the same. As the staggered EPR values of the 2 engines continued to steadily rise, within about 60 seconds of a problem first being evident, the gap between the recorded EPR values and the actual values for the left number 1 engine had opened up to about 0.34, while the right number 2 engine, the first to actually show any problem, was slightly less at 0.2. Admittedly not a huge error, but significant enough nonetheless to trigger the autothrottle's defaulting from max select into max alt. Let me explain. With the autothrottle in max select mode, it will adjust engine thrust as necessary in order to maintain the pre-selected cruise Mach number. If, while attempting to do this, the engine's EPR value reaches the computed EPR limit for this phase of flight, then the mode will automatically change to Mach alt and no further power will be applied, so as to make sure that the limit value is not exceeded. So specifically with regard Air Algérie 5017, in falsely believing that these EPR values were in fact genuine, the autothrottle had taken protective action once the EPR limit had been reached and commanded a slight, simultaneous power reduction on both engines. A subtle, insidious sequence of events evolving over a relatively short time frame, which unbeknownst to the crew, would in the very near future doom their aircraft and the lives of all those on board. Given that the only visible evidence of a problem existing at all were the slight EPR discrepancies between the 2 engines, coupled with intermittent activation of the Mach alt autothrottle mode, the fact that the aircraft's speed was still very close to its nominal value for the cruise portion of the flight meant that interpretation of all the telltale signs of potential trouble was less than straightforward. In truth, however, with the autothrottle's intervention and reduction of engine power from the normal cruise setting of about 80 to 85% N1 back to a value of closer to 77%, as indicated on the flight data recorder, it had reduced engine power by just enough so as to trigger a slow, almost imperceptible deceleration in the aircraft's airspeed. To explain why this will be so significant, it's best if we once again refer back to the general lift equation, which states that mathematically a wing's lift can be expressed as a function of the air density around it, the speed of the relative airflow over it, its overall area, and its positioning to that same relative airflow, in other words its angle of attack. Together they yield the equation lift equals a half rho v squared SCL. Given what's happening to Algérie 5017, as this deceleration continues, the value of v in our general lift equation will progressively get smaller, and so there will come a point where the amount of lift being produced by the wing has been sufficiently compromised so as to be no longer able to support the weight of the aircraft, and by definition, as this happens, the aircraft will start to descend. Only with the MD-83, its autopilot having been tasked with maintaining the aircraft's altitude, this simply won't be allowed to happen. Instead, as the value of v continues to reduce, other elements of the lift equation will be called into play in order to compensate, ensuring that the equation remains balanced. With the values of rho and s remaining constant throughout, respectively representing atmospheric density and wing area, this leaves only CL, or the angle of attack, as the sole remaining variable which can be called upon to restore this balance. Thus, as the aircraft speed continues to decrease as a result of the autothrottle's inadvertent underpowering of the engines, with the autopilot slavishly executing its assigned task of maintaining altitude, the wing's angle of attack will correspondingly start to increase, and this isn't a good thing. From the outset, as the aircraft's speed slowly began to bleed off, per the graph, the associated drag in the aircraft initially started to decrease as well, due in no small part to the fact that the aircraft wasn't actually pushing into the air mass ahead of it quite so hard anymore. As such, the initial rate of deceleration was actually reasonably modest, in fact almost imperceptible, at about a half a knot per second, indicative of just how subtle and insidious the change in circumstances were, at least initially. Closer examination of the graph indicates that as speed continues to bleed off, once the aircraft decelerates through the point of minimum drag, the dynamics of the situation utterly change in a dramatic and alarming way. The aircraft is now said to have started sliding up the back of the drag curve, or alternatively the back of the power curve. Let me explain. Up until this point, an excess of available engine thrust could have arrested the deceleration and restored equilibrium. However, due to the erroneous EPR values having already reached the cruise EPR limit, the auto throttle, instead of adding power, was actually reducing it, in an effort to prevent this limiting value from being exceeded. However, on decelerating through the point of minimum drag, a strange phenomenon occurs whereby the previous trend of drag reduction actually starts to reverse, meaning that efforts to arrest the deceleration will become more complicated the more this deceleration is allowed to continue. But this is where the corresponding increase in angle of attack starts to become problematic. Although this increased angle of attack will most definitely result in an increased production of lift, the fact that more of the wing's profile is being presented to the relative airflow means that along with this increase in lift comes a corresponding increase in drag. The problem now with Air Algérie 5017 was the fact that with the autothrottle believing it was unable to apply any further thrust on the engines to counter the continuing deceleration, this continuous reduction in airspeed was having the effect of driving the angle of attack to ever greater values, which in turn was still further increasing the drag on the aircraft, which still further hastened the rate of deceleration, driving the angle of attack still higher, and so on, as this spiral of events rapidly accelerated and continued unabated. Well, to say unabated would be somewhat misleading, with the rate of deceleration rapidly increasing as the aircraft slides up the back of the drag curve. There is a definitive point at which the whole lift equation actually breaks down. Looking at another graph of lift versus angle of attack, it can be clearly seen that as the angle of attack values increase, there is almost definitely a corresponding increase in lift being produced, but this can only be pushed so far. Beyond a certain value, the airflow over the wing will start to detach itself from the wing's upper surface and break away, resulting in a dramatic and sudden loss of lift. The wing is now said to have stalled, with the angle of attack value at which this occurs being termed the critical angle of attack. With the autopilot locked into maintaining level flight, early indications that this deceleration was heading towards an aerodynamic stall did start to present themselves to the crew. The fast-slow indicator on the respective primary flight displays, or PFDs, both showed the aircraft slow on the target speed, which hadn't changed from the initial pilot selection of Mach 0.74. Admittedly, this particular reference scale doesn't convey an awful lot, other than the fact that the actual speed of the aircraft is 10 knots or more below target. But even a cursory glance at the actual airspeed indicators as a result would have revealed that in the 4 minutes which had passed since the deceleration had begun, the aircraft's airspeed had fallen not by 10 knots, but rather 65 knots. And now at 213 knots, the instrument's pointer would have been almost vertical, certainly nothing which would have been considered in any way normal for cruise flight. Likewise, given the wing's ever-increasing angle of attack, the aircraft's pitch attitude had also manifested an increase of 4 degrees over the same time frame. Again, indicative of things not being as they should. But, along with the airspeed indicator itself, perhaps it was the autopilot's manipulation of the horizontal stabilizer which retrospectively should have been the clearest attention getter of all for the crew. With the airspeed depleting, in order to prevent the aircraft's nose from dropping and entering a descent, the autopilot had begun inputting counter nose-up inputs through the horizontal stabilizer. With the MD-83 Type, when such movement of the stabilizer exceeds half a degree, a buzzer sounds in the cockpit and is repeated every half degree of movement thereafter. Where this movement exceeds 2 degrees in less than 30 seconds, a synthesized voice calls out stabilizer motion, with the alert being repeated until such time as the stabilizer's motion has stopped. On foot of data retrieved from the flight recorder in the 4 minutes and 13 seconds between 0141 22 seconds and 0145 35 seconds, The investigation team believed that the tone indicating stabilizer movement would have sounded on no less than 9 to 10 separate occasions, with the oral stabilizer motion alert being triggered at least twice. In reality, Mojo needed to intervene fast, reduce the wing's angle of attack, and accept the resultant descent if he was to stand any chance of rescuing the situation. But as the seconds passed, neither he nor his first officer made any effort to do so. Having been passed off to the area controllers at Niamey, communication between the control centre and the aircraft had proven difficult to say the least. In attempting to deviate west around the adverse weather ahead, Mojo had unknowingly brought his aircraft to a point which was geographically on the very limits of Niamey's radar and VHF radio coverage. In fact, radio communications were being broadcast through a repeater station in eastern Mali, which was known to be unreliable, even when it wasn't being actively sabotaged by insurgents. Such was the political demographic in Western Africa at the time. Additionally, it would have been true to say that with the aircraft's relatively close proximity to the storm front up ahead, interference with VHF radio communication would have been more rather than less likely. Thus, having been transferred to the Niamey sector, in the 6.5 minutes immediately thereafter, records showed that there were a combined total of no less than 15 failed attempts between the aircraft and Niamey to establish two-way radio communication. Indeed, a Royal Air Maroc flight in the vicinity had also attempted to act as an intermediary, again without any success. Then at 01:44 and 29 seconds, Niamey picked up a faint female voice on the radio, identifying her call sign as being that of Air Algérie 5017. She stated that the aircraft was maintaining flight level 310 and deviating to the west around adverse weather up ahead. In response, he had instructed her to reset the flight's unique 4-digit transponder code, to pass her estimate for the Mokat intersection, and finally an instruction to make a further position report on passing the Gao intersection. He received no reply from the aircraft and the transponder code remained unchanged. This faint female voice, calling out from the turbulent skies above southern Mali, was to be the last communication ever received from Air Algérie Flight 5017. The final report surmises that the very act of trying to circumnavigate the storm ahead and their protracted communication difficulties had both conspired to distract Mojo and Kamari to the point where they had become blind to events which were unfolding, literally in front of their eyes. Then finally, approximately 6.5 minutes after 5017 had levelled off, it appears that the crew may have awoke to the impending danger facing. Between 01:44 52 seconds and 01:45 17 seconds, 2 high-amplitude Eeper oscillations were recorded on the flight data recorder. These manifested themselves not merely as independent Eeper fluctuations, but rather an oscillation of all engine parameters simultaneously, indicative of the fact that engine power itself had been increased. In fact, given that the Eeper value recorded during the first oscillation was in excess of the Eeper cruise limit which the autothrottle could command, the investigation team surmised that the crew must have intervened and manually adjusted the power levers themselves, most probably in response to a suspected Eeper problem. In fact, these actions were consistent with the items of the Eeper erratic or fixed abnormal checklist, which recommended movement of the thrust levers and subsequent observation of the effects on engine parameters. However, what this action wasn't appropriate to was corrective action in the context of an approach to stall type scenario. Prior to the second oscillation, the autothrottle was actually disengaged, indicative of the fact that the crew were now most definitely manipulating engine power directly themselves. Recorded Eeper values this time actually exceeded the theoretical maximum which could be extracted from the JT-80 engine, proof positive that the conditions underlying this erroneous Eeper phenomenon from the outset hadn't gone away. Despite the crew's belated efforts to address their perceived engine problems, the action taken had been far less than was actually required, had come way too late, and in truth had done nothing to address the root cause of their problems. At the moment of autothrottle disengagement, the indicated airspeed had dropped to just 203 knots, or Mach 0.56, sufficiently low to generate the low speed display on the FMAs. This normally would have prompted the crew to examine the overall energy state of the aircraft. But in the case of Algérie 5017, simultaneously yet another distraction presented itself. It was estimated that by this time the wing's angle of attack had increased to nearly 9 degrees, which in itself not only put the wing on the cusp of an aerodynamic stall, but given the fact that airflow over the wing's upper surface had started to separate, had also resulted in the inlet flow of air to the engine compressors being adversely affected as well, with uncommanded roll inputs also seeing the aircraft start to oscillate up to 4 degrees either side of the vertical. As such, both engines simultaneously began to surge. In other words, the normal longitudinal flow of air through the engine core had broken down. The rotational speeds of both the low and high pressure compressors N1 and N2 suddenly dropped, with a corresponding rapid fall off in fuel flow and recorded EPR. With airflow through the engine now all screwed up, the exhaust gas temperature or EGT spiked at a value quite literally off the clock. Both engines were now effectively useless, with recorded power outputs of close to idle. The separation of airflow from the wing as it approached stall gave rise to a very obvious and significant deterrent buffet, the aircraft's final warning of what was about to happen. Almost simultaneously, with events now developing at a frantic pace, as the aircraft's speed continued to decelerate to 200 knots, the stick shaker triggered, a tactile design feature whereby the control column is aggressively vibrated in order to draw the crew's attention to the impending stall. In the background, the oral stall warning was enunciated through the cockpit loudspeakers as the aircraft began its departure from the controlled flight envelope. On the understanding that the erroneous EPR values recorded shortly after topic climb had been the catalyst for all that had happened to Air Algérie 5017, the obvious burning question which needed to be answered was what exactly had caused this anomaly in the first place. Despite remarkably having recovered the cockpit voice recorder, or more accurately what was left of it, the investigation team were dealt an early blow. Although they were able to retrieve information from the recorder, they soon established that a failure of the recording head itself had meant that instead of one clearly isolated trace being available, multiple previous flights had been laid one on top of the other, creating an indistinguishable, useless mess of garbled audio. If they were to resolve the mystery of Air Algérie 5017, they would have to rely on what they could retrieve from the flight data recorder, the air traffic control tapes, and the combined evidence of both ground crew and other flight crews in the general vicinity. What was known for sure, and had been well documented, was the fact that the crew had identified significant weather ahead of them, and were taking proactive action in order to circumnavigate around it. The type of convective weather they had identified comes with many inherent dangers such as lightning, wind shear, turbulence and icing, for example. Had any or all played a part? Or was it a case that the aircraft had befallen some catastrophic technical failure, or even intentional sabotage? Retrieval and examination of the flight data recorder appeared to discount the latter, but did raise some concerns with regard to former threats. Although it was impossible to establish categorically whether the aircraft had been climbing through cloud as it circumnavigated the convective weather ahead, the absence of any telltale signs of turbulence combined with satellite imagery strongly suggested that updrafts which might have carried supercooled water droplets into the upper atmosphere were unlikely to have been encountered. These droplets, despite the low ambient temperature, remain in a liquid state while in suspension, freezing only when they come in contact with a solid particle, in this instance the aircraft structure itself. Yet, the investigation team were quick to note that supercooled water droplets weren't the only potential source of icing which could have threatened an aircraft the size of an MD-83. Some years previous, during the summer months of 2009, an Air France A330-200 series aircraft was lost to the South Atlantic after the crew has mishandled an erroneous airspeed indication, the root cause of which was determined to have been high-altitude ice crystals blocking the aircraft's pitot probes. Could something similar have happened to Air Algérie 5017? The truth is that the MD-83 was attempting to circumnavigate downwind of a fully mature thunder cell in the ITCZ. As such, one could assume that the anvil head of the cloud, as shown here, was by then well established. This characteristic anvil shape forms when the warm rising air of the thunderstorm reaches the stratosphere, where the air is typically warmer than the upper troposphere. At this point, called the equilibrium level, the updrafts within the cloud stop rising and instead spread outwards. For this reason, it's generally considered quite likely that ice crystals formed by these updrafts will be deposited within the anvil head itself. The danger for aircraft in the vicinity comes not only from direct penetration of the anvil, but also from attempting to fly under or downwind of the anvil, areas into which ice crystals can frequently be deposited by environmental upper-level winds. Furthermore, the danger this potential source of icing poses to an aircraft in flight is exaggerated by the fact that onboard weather radar systems are incapable of identifying the presence of these crystals due to their solid rather than liquid state. What this means is that, with no obvious threat being identified, the chance of a crew activating the aircraft's anti-icing system would be unlikely. With the MD-83 in particular, such anti-ice protection is achieved either by way of electrical or alternatively pneumatic heating methods. Cockpit windshields and critical probes affixed to the airframe for airspeed and angle of attack computation are electrically heated, whereas more vulnerable areas of the actual aircraft structure, namely the wing and horizontal stabilizer leading edges, and specifically the engine PT2 probes, are fed hot pneumatic air which is bled directly from the engine's compressor. The fact that the anti-ice system is designed to use bleed air from the engine's compressors means that activation of the system in flight will result in a reduction of the total amount of thrust being available from the engine. This reduction in available thrust will manifest itself as slightly lower N1 and EPR limit values, clear and definitive markers which are identifiable on the flight data recorder. Yet, when the investigation team retrospectively went looking for such evidence of parameter shifts, indicative of system activation, they came up empty-handed. Whatever the crew's action had been in the lead up to the accident event, with confidence, the investigation team had thus been able to say that the aircraft's anti-icing system had not been activated. In the absence of any usable cockpit voice recordings, the investigators were nonetheless unable to determine whether this non-activation was due to an oversight or alternatively a deliberate decision where their assessment of the prevailing environmental conditions hadn't warranted it. As is normal with any large-scale investigation into the loss of a commercial airliner, the investigation team would inevitably review similar historical incidents or accidents which may be of relevance to their investigation. In searching through the archives, one particular incident stood out and grabbed their attention. This incident had occurred nearly 12 years earlier in June 2002 to a Spirit Airlines MD-82 aircraft while cruising over Kansas in the US at flight level 330. With autothrottle engaged, the aircraft had been subjected to an inexplicable drop in engine RPM, resulting in a slow, continuous reduction in airspeed with a corresponding increase in angle of attack. This eventually had culminated in the activation of both the stick shaker and stall warning device, an almost carbon copy of what they had seen happen to Air Algérie 5017. With publication of its final report, the US National Transportation Safety Board surmised that the crew's failure to activate the aircraft's anti-icing system in advance of the incident had left the engine's PT2 probes susceptible to icing, most likely from ice crystals. The probe's suspected blockage had, they believed, thus given rise to erroneous EPR indications with an associated reduction in power being commanded by the autothrottle. Shocked by the apparent similarity between the two events, the investigation team, led by the French BEA, moved ahead to further examine how a similar icing scenario may have impacted upon 5017. They concluded that the erroneous EPR values, as experienced on the flight, could only have occurred as a result of either a technical failure in the measuring and transmission system of the EPR hardware, or alternatively by way of an obstruction, total or partial, of the engine's PT2 probes. Were the former to be the root cause of the anomaly, this would have required a failure of the EPR hardware on the right engine, then 55 seconds later a similar failure on the left. Furthermore, there would have also been a need for a simultaneous disappearance of both failures during the last 20 seconds of flight, while the engine RPM was rapidly increasing. Given the fact that both right and left systems are completely independent and share no common components, nor a common electrical power supply, the likelihood of such a coincidence of collective events was deemed to be extremely unlikely. Conversely, given the presence of such a significant storm cell close to the aircraft's flight path, as well as the apparent evidence indicating that the anti-icing system hadn't been active at the time the phenomenon occurred, made it far more plausible that an obstruction of the PT2 probe was the more likely cause. Furthermore, the reappearance of EPR values towards the latter part of the flight, with the aircraft descending through a much lower altitude and thus warmer environment, only strengthened this hypothesis. Specifically with regard to the PT2 probes fitted to the JT8D engine type, the supply of hot pneumatic air to warm these sensors is controlled manually by activation of two switches on the cockpit overhead anti-icing panel, one for each engine. The significant issue, however, with these probes is the fact that if left unheated, due to their geometry and relatively small diameter, they can be susceptible to obstruction by ice crystals, even if the crystal concentration is not exceptionally high. This is what had happened to Spirit Airlines Flight 970 back in 2002, and now it was starting to look ever more plausible that the very same thing had happened 12 years later to Air Algérie 5017. So, assuming for a second that this is what had happened, how does any potential blockage of the PT2 probe actually lend itself to the EPR anomalies which had been observed? You'll remember that the EPR values representing engine power output is derived from the ratio between the inlet pressure of air as it enters the low stage compressor compared to the outlet pressure of the exhaust gases as they leave the low pressure turbine. In other words, the PT2 value over the PT7 value. The important thing to grasp here is a concept, a principle of operation, not whether the units or ratios displayed are representative of the JT8D engine. That really doesn't matter. That being the case, let's say in normal flight the PT2 inlet value to the compressor is measured as a value of 2 units. Again, 2 units of what really isn't important. If we further assume, though, that the pressure output from the low pressure turbine is measured as 10 units, the ratio or EPR value will be read as inlet over outlet, or a value of 2 over 10, or 1:5 when expressed as a ratio, which we'll simply call a power output of 5 units. Now, let's partially obstruct the PT2 probe with imaginary ice crystals and see what happens. As the volume of ice crystals increases, the obstruction they cause will dramatically reduce the amount of air which will be allowed to pass through the probe's small inlet, and as a result, the sense pressure at the probe will be observed to decrease. Returning to our model, let's say as a result of this obstruction, the sense pressure at the PT2 probe is now reduced to a value of 1. If fuel flow to the engine hasn't changed in the meantime, and all other engine parameters have thus remained constant, the ratio between inlet and outlet has now become 1:10, rather than the previous value of 1:5. This, using our simplistic model, now represents a power output of 10 units, exactly twice the initial value. Thus, the partial blockage of the PT2 probe will manifest itself as an apparent increase in power output from the engine. Yet, from observation of all other engine parameters, we categorically know this to be untrue. In the case of Spirit 970, and now it would appear Algérie 5017, this apparent increase in power output had triggered the auto throttle to reduce the actual engine power, in a defensive move so to speak, in order to ensure that the EPR limit value for the cruise would not be exceeded and the engines potentially damaged. This reduction in power was of a magnitude which could no longer sustain continued flight at the respective cruise levels, and the resultant effect was the slow, continuous reduction in airspeed. It's worth noting that in relation to the MD-83's design, as with many older aircraft of the same era, stall warning devices used fixed angle of attack thresholds which were based on the aerodynamic characteristics of an aircraft at low altitude and flying at a relatively low Mach number. Certification requirements at the time mandated a 7% margin between the stall and the stall warning which would precede it. This warning could be attributed to the aerodynamic characteristics of the aircraft itself, for example the onset of buffet, or by way of a design feature, oral, visual or tactile, which would provide a clear, unambiguous warning to the crew of the impending danger. There was, however, a caveat, which stated that this 7% margin could be reduced if the stall warning possessed adequate characteristics in terms of clarity, duration, and distinguishability. Why this caveat was important was because of the fact that with an increase in altitude and Mach number, the wing's critical angle of attack will actually reduce. Therefore, if the warning thresholds are predicated on a fixed margin above a stall angle of attack computed for low altitude, low speed flight, as this critical angle of attack reduces with increased Mach number, it stands to reason that these buffer margins will be compromised. And indeed, with Air Algérie 5017, this is exactly what was observed. At time 0145, load factor on the aircraft was noted to decrease below 1G, indicative of the fact that the lift being produced by the jet's wings was now insufficient to adequately balance its own weight. Yet there was still some way to go before the critical angle of attack was reached. On the understanding that this occurred at a speed of 197 knots, the 7% margin we've talked about here would suggest that the first signs of the stall should have appeared at a speed of 211 knots. This speed was reached at time 0144 and 54 seconds, a full 19 seconds before the stall. Yet in reality, deceleration continued below the speed without any adverse indications being provided to the crew. In fact, the natural onset of buffet was the first indication to the crew that the angle of attack value had become critical. This occurred at 0145 and 06 seconds, as the aircraft decelerated through 203 knots, with the stick shaker being triggered 4 seconds later at 0145 and 10 seconds, just 2 seconds before the stall, as the aircraft decelerated through 200 knots. As the angle of attack increased above 9 degrees, the stall began to develop, with the full stall being recorded at 0145 and 12 seconds as the angle of attack reached 11.5 degrees. Of note was the fact that the oral stall warning was only sounded at 0145 and 13 seconds, technically 1 second after the stall had actually occurred. These margins were compared with those obtained during high-altitude stall tests undertaken for the MD-80 type certification, with comparable results being noted. That said, however, due to the caveat mentioned earlier, McDonnell Douglas nonetheless maintained that all regulatory requirements were complied with, although the investigation team were unable to find any written direction to crews highlighting this fact. So in short, although this 7% margin existed at low altitudes and slower Mach numbers, this was not the case at higher altitudes and Mach numbers typical of values experienced during cruise flight. In addition to the stick shaker, most regulatory authorities mandated that T-tail designed aircraft, such as the MD-80 series, be additionally fitted with a stick pusher, the function of which was to physically and aggressively force the aircraft's nose down, and thus reduce the wing's angle of attack should the crew themselves fail to do so. Regrettably, a further design feature of the MD-83 was the fact that this feature is actually disabled once the trailing edge flaps are retracted. So, just at that very moment where it was needed most, this final act of mitigation, which may well have saved the aircraft, was prohibited from happening, due simply to an ironic, short-sighted engineering design feature. In all likelihood, McDonnell Douglas design engineers most probably reasoned that such a stall event at cruise level was always going to be extremely unlikely, and were likewise most probably confident that crews would identify the developing situation and react appropriately. What this entailed was that in response to aerodynamic buffeting or activation of the stick shaker, both clear indications of an impending stall, the crew would have disconnected the autopilot and immediately pushed the control column forward, thus lowering the nose with a corresponding reduction in the wing's angle of attack. Under such circumstances, the pilot's efforts to lower the aircraft's nose would be assisted by a unique elevator power augmentation system, or EPAS, whose principle of operation was not dissimilar to that of a stick pusher. On the MD-83, each elevator is controlled by a tab, activated by the movement of the control column. But due to its T-tail configuration, when the aircraft is in a stalled condition, there may well be a decrease in the effectiveness of these tabs, and thus the positioning of the elevators, to the extent that recovery from the stall may prove difficult. For this reason, the EPAS system will act to assist the pilot when he or she applies a forward input on the control column, such that when these tabs are deflected by 10 degrees relative to the elevator, hydraulic power will be applied to a dedicated actuator, forcing the elevators into a maximum nose-down position. However, for reasons which will forever remain unclear, neither Mojo nor his first officer made any effort to either disengage the autopilot nor push the control column forward enough so as to activate the EPAS system. As the MD-83's wing entered full stall and lift rapidly dropped off, in a final effort to avert an impending descent, incredibly the aircraft's autopilot, still engaged, applied still more nose-up trim to the horizontal stabilizer. The angle of attack thus increased still further to 25 degrees, a full 13 degrees above the critical value, before finally the laws of physics took over. The aircraft rapidly pitched nose down and rolled uncontrollably to the left, its fall from the heavens to the desert below having violently begun. As the aircraft now descended uncontrolled through flight level 299, a loss of approximately 1,100 feet, its airspeed was recorded to have fallen to just 162 knots, or Mach 0.44, with the relative airflow now hitting the wing from almost directly beneath, consequently pushing its angle of attack ever upward. Finally, most probably the investigation team believed as a result of a belated crew intervention, the autopilot was disengaged, a full 25 seconds after triggering the stick shaker. It's worth noting that all previous approach to stall training scenarios which the crew had previously been exposed to in the simulator commenced with the autopilot disengaged, a fundamentally different proposition to what they had experienced in the accident flight. Algérie 5017 was now in a deep stall and most probably even at this altitude beyond saving. What this actually means is that specifically with regard these T-tail designs, if the angle of attack is allowed to reach excessively high values, the disturbed or stalled airflow breaking off the wing will act in such a way so as to blank the pitch control surfaces on the horizontal tailplane, meaning that no matter how hard the pilot pushes forward in order to lower the nose, his or her efforts will be ineffective. In short, recovery from these deep stalls is thus impossible, and hence the philosophy behind incorporating a stick pusher into the design of this aircraft group in the first instance. The physical characteristics of the MD-83 stall behaviour eventually resulted in the nose continuing to fall through the horizon, with subsequent pitch and roll values being subjected to significant changes. They respectively reached values of 80 degrees nose down and 140 degrees of roll to the left, essentially an inverted spiral dive from which there was no recovery. As an aerodynamic stall is solely the result of the wing's angle of attack exceeding its critical value, the converse is true, in that to unstall the wing, the angle of attack must be reduced to a value below the critical value, so as to allow the relative airflow reattach itself to the wing's camber, thus restoring its ability to reproduce lift. Notwithstanding the comments just made in relation to the T-tail design, categorically the flight data recorder showed that for the majority of the descent, one or both of the flight crew members had actually maintained consistent inputs on the cockpit controls in an effort to pitch the nose up, not down, with a consistent roll input being made to the right in an effort to counter the aircraft's uncommanded left-hand spiral. As 5017 fell uncontrollably towards the Saharan sands below, 20 seconds before impact the engine surge conditions suddenly stopped, and both simultaneously showed a marked increase in RPM, with parameters indicating values of almost full power. This the investigation team attributed to the wing's angle of attack having been reduced from 23 degrees to 8, most probably as a result of belated control inputs on the part of the crew, thus re-establishing a steady airflow through the engine's compressors, with the increased density of the lower atmosphere making a positive contribution as well. Despite this, however, the wing was never unstalled, and as a result Air Algérie 5017 impacted the scrubland of southern Mali at 0147 local, just 32 minutes after departure. The recorded parameters painted a chilling picture of the aircraft impacting the ground in a nose-down attitude just 30 degrees from the vertical, with a very shallow bank turn to the left and a descent rate of nearly 39,000 feet per minute. With the aircraft's departure from flight level 310, impact with the desert scrub below had taken less than 50 seconds. Upon impact, the aircraft and all 116 souls on board were completely obliterated. The point of impact lay roughly in the area bordered by Burkina Faso, Mali and Niger, an area of West Africa even to this day troubled by conflict and insurrection. The last radio contract that Niamey controllers had with 5017 was at 0144 and 28 seconds, a mere 3 minutes before the accident. This interaction established that the flight was maintaining flight level 310 and manoeuvring to avoid convective weather in the area. The controller had asked the crew to change their 4-digit transponder code to give their estimated arrival time for overhead MOCAT, and to call back with a position report on passing Gao, none of which was acknowledged or actioned by the crew. The controllers knew from experience that aircraft west of the Apepo-Gao MOCAT route were likely to temporarily drop off their radar screens and experience significant difficulties with two-way radio communication, only to reappear as the flight approached the latter MOCAT waypoint. On cue at 0147, Air Algérie's radar plot did disappear from the Niamey controller's screen. The aircraft was at this stage 30 nautical miles west along the Apepo-Gao route, at a point approximately 95 nautical miles from Gao and 250 nautical miles from the November Yankee Niamey radio beacon. Just over 5 minutes later at 0152 and 45 seconds, the Niamey controllers estimated that 5017 should have passed the Gao intersection. On any other day, this should have triggered an automatic handover to the next controller in sequence, working the northern sector. But unable to complete the handover, the initial controller instead reported that 5017 was still not visible on radar and that he was unable to establish any communication with it. Little did he know that Algérie 5017 was already gone. Still not unduly worried, over the next 7 minutes between 0155 and 0202, Niamey attempted to contact 5017 on both VHF and HF radio frequencies, while also attempting to elicit the help of a number of aircraft in the area to act as airborne relay stations, all without success. At 0230, Algérie 5017 was forecast to pass overhead the MOCAT intersection, the boundary between the Niamey and Algiers controlled airspaces. The flight should have reported in and accepted its handover from one controlling agency to the next, yet neither controlling agency had now any contact with the flight, and its anticipated return to the radar scopes simply hadn't happened. With 45 minutes now having passed since the MD-83 had impacted the deserts of southern Mali, controllers on both sides of the boundary grew ever more concerned as to where the aircraft actually was. In such circumstances, guidelines within the text of ICAO Annex 11 provide a clear and unambiguous timeline as to how any potential search and rescue operation will be undertaken and conducted. The first phase of such an operation is termed the INSERFA, or uncertainty phase, which should have been established after an elapsed time of 30 minutes following a missed mandatory position report. In the context of Algérie 5017, this should have occurred at 0230, 30 minutes after the aircraft was supposed to have reported passing overhead the MOCAT intersection. However, for some inexplicable reason, this never actually happened. An upgrade to the ALERFA, or alert phase, should have happened following the INSERFA phase, where subsequent attempts to contact the crew had proven unsuccessful, or inquiries of other relevant sources had failed to shed any light on the aircraft's whereabouts. At the suggestion of the Algerian controllers, Niamey Air Traffic Control Centre activated this phase at 0330, a full hour and 45 minutes after the aircraft had actually crashed. Finally, the DISTRESSFA, or distress phase, is triggered on foot of the alert phase, where more widespread inquiries have failed to provide any further information on the aircraft's whereabouts, or when the fuel on board is considered to be exhausted. This phase may also be established where information is received which suggests that the operating efficiency of the aircraft has likely been impaired, to the extent that a forced landing has either likely occurred or is likely to occur. The distressful message was sent from Miami at 0438 local, almost an hour and 10 after the alert phase had been triggered, and 2 hours 50 minutes after the accident itself. Upon its receipt, the Algiers Control Centre queried Miami as to when and where radar contact had been lost with 5017. On the basis of what little information was available, the two controlling agencies between them estimated that the crash, which was now becoming all the more probable, had most likely occurred between the Gao and Mokat intersections. Almost an hour after sunrise at 0632, Miami requested the support of the French Air Force stationed in the area, who responded favourably. As such, an hour and 45 minutes later, Miami was informed that French military aircraft were in the air, while a further two Cessna 208 Caravans of the Niger Air Force were also standing by if needed. At about the same time, a crisis management team had been gathered in Burkina Faso. Although the French Air Force had been informed that the likely location of the wreckage would be somewhere between the Gao and Mokat intersections, the team in Burkina Faso presented evidence at 13:08 that afternoon, which questioned that assumption. Unlike their colleagues in Niamey, who had lost radar contact with Algérie 5017 as it deviated further to the west and beyond the coverage of their radar, the controllers at Ouagadougou had not, and even though the aircraft was no longer under their jurisdiction, they could nonetheless still monitor its progress on their radar equipment. With the complete readout of the aircraft's altitude, speed and heading, the authorities in Burkina Faso were thus of the belief that the aircraft had gone down near the remote settlement of Boulkaisi in southern Mali. As such, a helicopter from the Burkina Faso Air Force was dispatched from Ouagadougou at 1500 on the afternoon of July 25th, successfully identifying the remains of Air Algérie 5017 nearly 3.5 hours later, more than 16 hours after the aircraft's disappearance. The location of the crash was fixed at 15 degrees 8 minutes north, 1 degree 4 minutes west, a spot in the Sahel sublands approximately 80 kilometres southeast of the town of Gossi and 160 kilometres southwest of the town of Gao. Given the local security concerns, examination of the wreckage could only take place once the immediate area had been secured by the French military, a process which was to take almost 3 days. The area in which the aircraft's wreckage was finally located was described as being generally flat, with an average elevation of 270 metres or 885 feet above sea level, and consisting of bedrock which was covered by a 50 centimetre layer of sand and clay. The only visible obstacles in the area consisting of sparse vegetation not exceeding about 5 metres or 15 feet in height. The force of the impact had created a crater, nearly 35 metres or 115 feet wide, 11 metres or 36 feet long, and 1 metre or 3 feet deep. The wreckage was spread over a triangular-shaped area, the length of which was about 420 metres or nearly 1,400 feet, the summit of the triangular wreckage field marking the aircraft's point of impact. This debris field spread outwards from the point of impact to a maximum width of about 340 metres or 1,100 feet, along a mean compass axis of 090 degrees magnetic. All of the evidence pointing to the fact that the aircraft had impacted the ground at an extremely high rate of descent and speed. In fact, with regard to the aircraft's attitude at the moment of impact, it was noted that trees in the area, about 5 metres or 15 feet in height, and located only 10 metres or 30 feet from the point of impact, remained intact and undamaged, indicative of the fact that the MD-83 had hit the ground at a very steep angle indeed. The investigation team ultimately concluded that Air Algérie 5017 was lost due to the aircraft's autothrottle commanding a decrease in engine power, as a result of an erroneous and false indication of increasing engine NEPR values. These erroneous values, it was believed, had been generated as a result of the localized obstruction of both engines' PT2 probes, most probably by ice crystals, a condition which was facilitated by the crew's failure to activate the aircraft's anti-icing system. The autopilot then gradually increased the aircraft's angle of attack in order to maintain altitude, until the aircraft subsequently stalled, with the crew taking no proactive action to intervene. Thus, the stall condition was not recovered, with the aircraft descending in a nose-down, left-bank spiral dive until impact with the ground below. On foot of the Spirit Airlines incident of 2002 and the loss of West Caribbean Airways Flight 708 in 2005, another MD-82 accident resulting from high-altitude stall, a number of safety recommendations had already been proposed in relation to operation of this aircraft type in atmospheric conditions which may be conducive to icing. It had already been suggested that pilot training syllabi in the context of stall recovery should be made more relevant and representative of the real world. Traditionally, such training was quite contrived, with scenarios predominantly staged at lower altitudes where handling characteristics are fundamentally different from operations at high altitude. Furthermore, the fact that the lead-in times for activation of stall warning devices was compromised when one ignores the influence of Mach number on the critical angle of attack meant that pilots experiencing an approach to stall event at altitude had considerably less time to react, and so, by any rational reasoning, safety margins had been reduced. This, they argued, needed to change. There were also recommendations made in relation to better educating pilots as to the dangers of encountering ice crystals at altitude, and a recommendation that manufacturers strive to develop an effective system which will specifically alert pilots to any obstruction of the PT-2 probe. Part of this focus was also to be directed towards improving a crew's ability to correlate N1 compressor speeds with EPR values, so that power settings can be validated and potentially erroneous indications quickly identified. These recommendations were again largely echoed, with final publication of the report into the accident of Air Algérie 5017. Yet the French BEA and Mali authorities went a step further. Collectively, they pushed the manufacturer to carry out a feasibility study as to the possibility of installing a permanent anti-icing system for the PT-2 probe, independent of any crew activation requirement. Until such time as this could be done, they strongly advocated that the aircraft's anti-icing system be activated manually any time the total air temperature dropped below 6 degrees centigrade, irrespective of whether visible moisture was perceived or not. Although a fresh approach to stall training had already been called for, this report went further in advocating the promulgation of information relating specifically to autopilot behaviour. They were of the opinion that an autopilot's failure to disengage under such circumstances, and its potential to make a bad situation a whole lot worse, was a little-known design feature of the MD-83, and that fact needed to be communicated to those pilots flying the type. In fact, they went so far as to suggest that this very design feature should be retrofitted out of the aircraft, and that instead, an approach to stall scenarios should always result in the automatic disengagement of the autopilot, thus removing any potential barriers to a successful and efficient recovery of the aircraft. Regrettably, investigation teams the world over can only suggest, advise and recommend, based on what they have learnt, so that the industry as a whole is collectively safer for all of us. Whether these changes ever see the light of day is an issue for the regulators, but given their age and the fact that the worldwide fleet of MD-80s was already in decline, the wheels of change would not move very fast. This was the complete story of Air Algérie Flight 5017, ironically lost as a result of ice in the desert.